Okay, let us start. So today, for a while, there is only one student offline. Nobody's online. Very strange. Okay. Nevertheless, hello everybody. And first of all, I have to inform you about exam program. I wrote it last week, but so they announced it on the site of our department, but unfortunately on Monday I met with one of your seminar teachers, and he said that you are not able to finish power series in seminars. So I decided to cancel big part, namely power series, and it means the program is replaced by another one, but I checked today morning, it is still old version exists. So the final exam program does not include questions about power series. They will be moved to third semester exam, as it happened with Taylor formula and so on from the first semester, right? So Taylor formula, L'Hopital rule was before. Taylor formula and applications for extremum. I gave them during lectures of the first semester, right? But unfortunately, I didn't include it into the program for the first semester exam, hence it is included into the second semester. And the same situation will happen with power series. Again, just now I'm given parts of power series topics, but they will be included into the third semester exam. Okay, so I would like to start with completion of 27.1 around binomial series. So we studied the behavior of the following series. For x equals to plus or minus 1. And before we started, we proved absolutely convergent this series at both points for alpha greater than 0. In fact, of course, you can include 0, but it will be not a series. And so now the question is about convergence. Conditional convergence, because absolute convergence is studied for alpha less than 0. That is the question. And I proved that for alpha less than 0. So if we denote, for example, we started to consider x equals to 1. Oof, I forget which letter I used. No, I didn't take it with me, unfortunately. I don't. So maybe it will be different letter, but I hope it's the same. An equals to alpha minus 1, so on alpha minus n plus 1 over n factorial. And we started the ratio, which is equal to alpha minus n over n plus 1. And modulus of this expression is equal to n minus alpha over n plus 1. And this is less than 1 for alpha, for which values of alpha, minus 1, 0. That was observed during last lecture. Hence, we can try to use Leibniz So let us consider Leibniz test. Let me recall what is it. So we know that such a series converges when Bn is monotonically and infinitely small. Monotonically infinitely small sequence. So let us try to understand what happens for our case. So what is about signum of An? If alpha is between -1 and 0, we have every term in the product is negative, hence that is -1 to the power n. So we have n negative terms, so we obtain the sign equals to -1 to the power n. So for x equals to 1, our binomial series is, in fact, I considered it, but I want to recall what happened. And so 1 plus 1 power alpha equals to sum n from 0 to infinity an. So we can write as -1 to the power n modulo an. And the sequence of modulo of an is decreasing. So the question is if the limit equals to 0. So let us consider this expression. So what is modulo an? Modulo an is modulo alpha times modulo alpha plus 1, so on, modulo alpha plus n minus 1 over n factorial. Or we can write it as a product. K starts from 0 up to n minus 1, modulo alpha plus k over k. Oh, sorry. From 1 up to n, and then, yeah, k minus 1. That is better. Otherwise, not a good idea. That is the expression for our modulo of an. So the question is if this product tends to 0. And that is equivalent to the question when logarithm of modulo an tends to minus infinity. Because the logarithm of 0 is minus infinity, roughly speaking, right? And so what is logarithm of modulo? That is the sum, okay, from 1 up to n of logarithms modulo alpha plus k minus 1 over k, or I can rewrite it as sum k from 1 up to n logarithm 1 plus modulo alpha minus 1 over k. So what we have here, we have a partial sum that is a partial sum of the series k from 1 up to infinity logarithm 1 plus modulo alpha minus 1 over k. So the question about limit equals to minus infinity is related to the value of this sum. So we want to be sure that this sum is infinite. And what means infinite sum of a series? It means that the series diverges, right? So hence I can but be careful. I should write in more details. Diverges minus infinity. So we know that usually what means divergent series? It means that partial sums have no limits, right? Or limit is infinite. And we want to have precisely minus infinity as a limit. Nothing else. So, but to study the series, we can use Taylor formula for logarithmic function. So it says that is modulo alpha minus 1 over k plus, not plus, minus, modulo alpha minus 1 squared over 2k squared plus little o of 1 over k squared as k tends to infinity. Now, we know that the series converges. And the series diverges to what? Remember, now I consider the case alpha is between minus 1 and 0. If alpha is between minus 1 and 0, this numerator is negative, right? So this is a negative number. We know harmonic series diverges to infinity, to plus infinity, and we multiply by minus. So diverges to minus infinity. Hence, that is indeed true for alpha from minus 1 to 0. And finally, we conclude that indeed this expression is valid also for alpha greater than minus 1. During last lecture, we checked it for alpha positive. Now, it turns out that it is valid for alpha greater than minus 1. So, last question, what happens for alpha less or equal to minus 1? And also, x equals to 1. And also alpha less than 0, x is minus 1. So these are two last questions. And I want to prove that the series diverges. Then the binomial series diverges. Why? For example, let's start with x equals to 1. Look, if alpha is strictly less than minus 1, I don't want strictly less. For a while, strictly less. I will say a little bit later about alpha equals to minus 1. At the moment, I want to consider alpha less than minus 1. So if alpha is less than minus 1, then what happens here? Alpha is less than minus 1. Then this number is positive, right? Alpha is negative, less than minus 1. Then modulo alpha greater than 1, right? Modulo alpha greater than 1. So alpha less than minus 1. Hence modulo alpha greater than 1. And then this series diverges to plus infinity, right? And if it, so logarithm, the series of logarithms diverges to plus infinity, hence limit of modulo n is also plus infinity. So hence limit of modulo an equals to plus infinity. So by term test, we have divergence of the series, right? Okay, for alpha equals to -1, the situation is slightly different. For x equals to 1, right? Namely, what happens? Look, it means 1 plus x minus 1. I want to consider this series. Recall that the binomial series for that case looks like that. And if I'll substitute, -1 to the power n, right? Yeah. If we substitute x equals to 1, then we have equality. And we know this series diverges, but by different reasons, namely now limit of term is not infinity, but it is not 0. So the claim is also valid for alpha equals to -1. And lastly, for x equals to -1 and alpha negative, what happens? Look at the series from the beginning. If alpha is negative, right? Substitute x equals to -1. We have 0 in negative power, right? So it's infinity. And it means the series cannot be convergent. Since we know by second Abel theorem, once we have a convergence at the point of the interval of convergence, then the sum should be continuous at that point. And the function is infinity at -1. Hence, it's impossible. So in the rest cases, our binomial series diverges. That is completion of the section 27.1. So now we can describe the behavior of the binomial series. So it's absolutely convergent for alpha greater than 0 at both ends of the interval, and it is conditionally convergent for alpha from -1 to 0 at x equals to 1. Let me summarize it. So, summary. Summary. One plus x power alpha sorry. And alpha, I forget. I'm sorry. And alpha. X power n. Is absolutely convergent for alpha greater 0 modulo x less or equal to 1, and for alpha less than 0, modulus strictly less than 1. And conditionally convergent for alpha from -1 to 0, x equals to 1, x equals to 1, and divergent for other alpha x. I should alpha belong to r minus integers and 0, x in r. Because for alpha natural or 0, we have no series. That is why no sense to talk about convergence. Okay, that's all for section 27.1, and we can start section 28.1. Today's section is complex exponent and trigonometric functions. Here, let me recall. We had a definition for e to the power I phi as follows. Phi in real. That was definition of the exponential function for such values of the argument. So, if z in complex plane, then it's natural to define e to the power z as e to the power x times e to the power iy, or in other words, e to the power x times cosine y plus I sine y. And also, once we define exponent like that, it's natural to generalize Euler formulas. So we had Euler formulas like that. Right? Then we can define cosine z equals to e to the power iz plus e to the power minus iz over 2. Sine z equals to e to the power iz minus e to the power minus iz over 2i. Now, those functions are defined for arbitrary value, for arbitrary complex value. Okay. These are complex exponential and trigonometric functions. Now, what's about properties? Properties. In fact, it's easy to check that, for example, I'll check this property of exponential function. And okay, I'll check the first one. So e to the power z1 plus z2. If I'll substitute x1 plus I y1, x2 plus I y2 in terms of real and imaginary parts, then we can replace it as follows. And using the definition, we can rewrite as e to the power x1 plus x2 times cosine y1 plus y2 plus I times sine y1 plus y2. And what is it? That is e to the power x1 plus x2. Okay, I may rewrite like that by properties of usual real exponential function. And here cosine y1 times cosine y2 minus sine y1 times sine y2 plus I times cosine y1 sine y2 plus cosine y2 times sine y1. And that is precisely e to the power x1 times cosine y1 plus I times sine y1 times e to the power x2 times cosine y2 plus I sine y2. Just open brackets. So cosine y cosine y2, we have it. Then I sine 1 times I sine y2 gives minus sine y1 sine y2. And lastly, I sine y1 cosine y2 we have, and I sine y2 times cosine y1 also we have. So and these are precisely e to the power z1 times e to the power z2. That is what we wanted. And analogously, we can check division property. So that is quite easy. Okay. Let me erase everything. Oh. Okay, now theorem 1 in this section. For any complex value of z, the expansions e to the power z equals to sum n from 0 up to infinity z to the power n over n factorial. Cosine z equals to minus 1 to the power n z to the power 2n over 2n factorial, and sine z equals to sum 0 to infinity minus 1 to the power n z to the power 2n plus 1 over 2n plus 1 factorial are valid. So the result is that we can not yet. So proof. We use the definition. So e to the power z is by definition that one. And we can use Taylor series for both exponential and trigonometric functions. So we have sum n from 0 up to infinity x power n over n factorial times sum m from 0 up to infinity minus 1 to the power m y to the power 2m factorial plus I times sum m from 0 up to infinity minus 1 to the power m times y to the power 2m plus 1 factorial. Now we can multiply those two series. How? Why? Better to ask firstly why we can multiply those two series. As we know, not both, in fact, we have three series here, right? All three series have infinite radii of convergence. So radii of convergence are infinity for each of those three series. Hence, each of those series converges absolutely. And we know that we can multiply convergent series, absolutely convergent series, without taking, we don't care about order of multiplication, right? So but before to multiply, I want to unify those two series. So let me do it like that. I can write them as follows. Look, maybe k from 0 up to infinity, iy power k over k factorial. That is how I can add those two series. Why? Because look, here what I have. Look, iy to the power 2m, what is it? That is I to the power 2m times y to the power 2m, I squared power m, y power 2m, minus 1 to the power m, y power 2m, right? And also, here you see I have extra multiply I, so I y power 2m plus 1 equals to I minus 1 to the power m times y to the power 2m plus 1. Right? And it means that both series, they have precisely the same numerators, right? And denominators 2m factorial, 2m plus 1 factorial, so it means we have the summation over all natural values of k and also 0. Okay. Now, as I said, both series have infinite radius of convergence. Hence, both are absolutely convergent for all values of x and y. And we can multiply in arbitrary order. And I prefer to do it for Cauchy multiplication. So what is Cauchy multiplication? Here, Cm, where Cm is the sum, let's say j from 0 up to m. We should take jth term x to the power j over j factorial from here, and number m minus j from the second one. So I y power m minus j m minus j factorial. Okay, but then look, I can rewrite as follows. Look, I can write it 1 over m factorial times sum j from 0 up to m factorial over j factorial m minus j factorial x to the power j iy to the power m minus j. And that is precisely binomial formula, right? These are binomial coefficients. So we have 1 over m factorial x plus iy power m. And recall, x plus iy is precisely z. So z to the power m over m factorial. And so you see, we started with e to the power z, and we obtained e to the power z equals to sum of Cm, where Cm are equal to z power m over m factorial, right? So it means the first expansion is proved. The first expansion is proved. Oh, expansion. The first expansion is proved. Now let's consider the second expansion. the second expansion. So for cosine z, recall the definition, e to the power iz plus e to the power minus iz over 2. So we substitute 1/2 of the sum iz to the power n over n factorial plus 1/2 sum of minus iz power n over n factorial. And now look. Obviously, for odd n, right, those two terms will be cancelled, right? So what remains? Only even terms are preserved, and for n even both are equal, right? And it means we can cancel these 2 1/2. So we have sum for m equals to 0 up to infinity iz to the power 2m over 2m factorial. Only even terms are preserved, and I to the power 2m, as I did here, right? We considered before, so that is precisely minus 1 to the power m z to the power 2m over 2m factorial. That is the second expansion, right? And now the third one, for the sine z, e to the power iz minus e to the power minus iz over 2I. So 1 over 2I sum of iz power n over n factorial minus 1 over 2I sum minus iz to the power n over n factorial. Now you see, when n is even, both terms coincide, and we have minus here, so they are cancelled. For n even, only n odd remain. So 2 equal terms, it means cancel 1/2. We have 1 over I times sum n from 0, m from 0 up to infinity. So only odd terms remain. iz to the power 2m plus 1 over 2m plus 1 factorial. And now iz to the power 2m plus 1, I computed, I times minus 1 power m, cancel I, and we have precisely what we wanted to prove. And the theorem is proved completely, right? Now, let me make a precaution. So, be careful. Be careful what I mean. Look, when I mentioned properties of the exponential function, right, I said nothing about the following property. Right? We have such a property of real exponential function. But there is no such property for complex exponential function. Why? Because for complex exponential function, so we defined exponential function e to the power z, right? Yeah, e to the power z. So complex exponential function is defined only with base e, no other bases for a while, right? And that is the point. So for complex functions, there is no good way to define exponentials in general. So in fact, the reason lies in logarithms. So okay. Let me clean the blackboard. I forget about break, but let it be break when I am erasing. Very short. So what is logarithmic function? What is logarithm? Logarithm is an operation which is opposite to exponent. Exponenting, better to say, right? So, for example, if I want to determine logarithm, like logarithm with e, with respect to e, then for logarithmic function, this should be like a solution of this equation, right? But remember, so if w is, okay, which letters to use, u plus iv, right? Then I can rewrite like this, e to the power u times cosine v plus I sine v. What it means, this equality? It means that once I add, so v, I consider instead of v if I replace it by this expression, v plus 2k pi I, where k is integer and I is integer unit, then what happens? Substitute here with the same, right? Value of w. Value of z, sorry, right? So it means if I want to determine logarithm of z, right? If I have found somehow u and v, right? Then after adding 2k pi I to v, right? I have also the solution of the same equation, right? So it means that we have infinitely many values of logarithm for an arbitrary complex number. You will consider it in more details in complex analysis later. But I want to explain the difference between real and complex analysis. Here is the first point when you can see it, right? So very simple property is not valid. Why? Because now how to define a to the power z? If we know exponential function, the natural way would be right like that, right? But now logarithm has infinitely many values, right? And it means a to the power z is also has infinitely many values. It means when you write expression like that, right? Here you have some complex number, right? So how you can define it? You can define it as e to the power z2 times logarithm of e to the power z1. And now there are infinitely many values of this logarithm, including z1, right? So it means that this expression has infinitely many values, including e to the power z1 times z2. So they are quite different. This is well defined, right? But that has infinitely many values, including that one. So you cannot write equality because these are different expressions in general. Okay. So this was a rather short section. And now I want to start the last section. I'll finish it tomorrow. So 28.2. Analytic functions. Taylor theorem. We had Taylor theorem in the first semester, but now that is quite different. And so let me give a definition. So definition. F of x is analytic at a point x naught real if f can be represented by its Taylor series in a neighborhood of x naught. So it means that Taylor series of our function should have a positive radius of convergence, and the function should be represented by its Taylor series. Okay, we had an example of real analysis. F is analytic, hence, by definition, F is infinitely differentiable. But converse is not true, right? There was an example, you remember, f of x e to the power minus 1 over x squared, x not equals to 0, 0, x equals to 0, right? The function is infinitely differentiable, but not analytic, because its Taylor series is identically 0. So it cannot be represented. But for complex analysis, as you will see later in complex analysis course, that is quite different. Okay, of course, I should be careful. You see, here I didn't say where it is analytic. In a domain, should be right. But okay, for a while I didn't give a definition of what means analytic in a domain. Analytic in a domain means analytic at every point. But I don't want to use this definition for a while. You will understand a little bit later. So analytic, but here I should write it. Okay, here, of course, domain should be the same in the domain. The same. So you see, for real analysis, from analyticity follows infinitely differentiability, right? But of course, also it follows for complex analysis as well. But conversely, it's sufficient to ask just one derivative for complex analysis, and then you have analyticity. That is quite different. So you see, there are differences between real and complex analysis. I mean, look, such a simple property was valid for real analysis, but not valid for complex analysis. But from the other side, it is essentially better, right? In that sense. So you see, there are some aspects where complex analysis is better, and I would say in most parts it is better than real analysis, but you will study it later, not with me. Okay, now I want to explain why I tried to avoid this indication where it is analytic at a point or in a domain. So look, we represent our function by Taylor series, right? Okay, I'll write like radius of convergence is positive, so it converges for such values of R. r is positive. And then, very natural question. What is about take arbitrary x from this interval, right? Is it true that our function is analytic at this point as well? And that is indeed the case. So if you represent our function by a Taylor series with such a positive radius of convergence, then it is analytic at every point of this interval for sure. And that is in fact Taylor theorem, which I plan to prove tomorrow. But today I would like to formulate a lemma theorem, let it be theorem, which will be used tomorrow. So theorem 1, right? Given double sequence. Okay, I didn't define what means double sequence, but Aij such that okay, let me, which indices I use? J from 1 up to infinity. And not such, suppose. Given, better to say suppose. And the series converges. Then doesn't matter how to sum up that double sequence. So you see, we have two indices. Double sequence means that we have two indices now, right? And in fact, this is highly non-trivial question when we can change the order of summation. In general, it's impossible. But you see, if we put this extra supposition, then we can change the order of summation. Okay, proof. Proof. Put xn equals to 1 over n equals to 1, 2, so on, and x naught equals to 0. And then consider such a set x naught, x1, x2, so on. That is a number set, right? Now define functions. Okay, what are functions? F I of xn equals to sum j from 1 up to n aij. So here I varies from 1 and so on, and 1 to so on. Also, f of x, f I of x naught equals to, by definition, the sum of the series aij, I from 1, so on. Why this series is convergent? Because if you put modulus, we know it is convergent by supposition, right? Hence, it is absolutely convergent for arbitrary fixed I. If we fix I, right? If we fix I, we have with fixed I, we have usual series which is absolutely convergent. So this is absolutely convergent series, hence it is convergent, and this number is well defined, right? So we have defined infinitely many functions, right? Moreover, what is about limit as n tends to infinity fi of xn? I is fixed. So if n tends to infinity, right, we know the series is convergent. These are partial sums, so they tend to that one, right? Fi of x naught. Hence, fi are continuous on E for every value of I. Why? Because look at the set E. It consists of isolated points x1, x2, and so on, right? Plus one limit point, x naught. 0 is limit point of that sequence, right? So it means that our set E contains only one limit point, right? And continuity over this set is satisfied when we have such equality. Okay, so we have a sequence of continuous functions. Moreover, fi of xn is less or equal the sum modulo aij, so less or equal bi for every value of I and n, right? Yeah. So by Weierstrass test, we deduce that the series I from 1 up to infinity fi of xn converges uniformly on E. Yeah, in fact, I can include here n equals to 0 as well, right? For n equals to 0, we have here infinity, and it means also same inequality is true. So for arbitrary n modulo less or equal bi, and the series of bi converges, hence by Weierstrass test, this series converges uniformly on E. And from those two suppositions, what we deduce by uniform limit test, uniform limit theorem, limit theorem. I'll use this short name. I call it somehow differently. Uniform continuity, uniform convergence and continuity, something like that it was called. In the program I gave this title for that theorem. So that is a theorem which says that if we have a sequence or series of continuous function and this sequence or series converges uniformly, then the limit is also uniform. That is shortly, let me call it uniform limit theorem shortly. So uniform limit theorem, then it says that the sum of this series, and what is the sum of this series? Fi of x is continuous on E. Okay, let me denote it by g of x, this sum. So this sum is continuous function on E. Okay, then what means continuous? What means continuous? Continuous means that, okay, here it's not, let me, like that. So it implies that g of x naught equals to the limit g of xn. Okay, let me write this equality in detail, right? What is it? What is it? J of x naught. So I should substitute here x naught. I should write the series I from 1 up to infinity fi of x naught, right? Okay, what are fi of x naught? Here they were defined. Let me substitute them. The sum j from 1 up to infinity aij. So that is nothing else but j of x naught. J of x. Then it is equal to the limit as n tends to infinity j of xn. Let me write what are j of xn. Limit n tends to infinity sum I from 1 up to infinity fi of xn. I substituted here x equals to xn. Then what are fi of xn? They were defined here. Limit as n tends to infinity sum I from 1 up to infinity sum j from 1 up to n aij. So here we have finitely many terms. If we have finitely, so we may consider it as a finite sum of series, right? Because every term of this series is a finite sum. And if we have finitely many series, then we can change the order without any problem. So I can change the order, rewrite it as follows. And now look what we have here. Limit of partial sums. We know it exists, right? Hence I can write it as a sum of series and look, that one and this one, they're equal, right? And the theorem is proved. Theorem is proved. I like this proof. It is taken from Baby Rudin Principles of Mathematical Analysis. Okay, that's all for today. Thanks for your attention. And still nobody is online. Very strange. Really? Yeah, but so link is connected with room. I see. I see. But you have an information about the room, right? Okay, so you could. Yeah, I understand, but yeah, you had an option to come, just to come, right? I hope so. Okay, then bye.